I'm going to do a demonstration and some measurements with ball bearings, which have very precise radii, very well known, which I'm going to drop into syrup. And we have chosen for that Karo light corn syrup. It may interest you that 2 tablespoons is 180 calories. I needed to know more for this demonstration, and so I had to do my own homework on it. But at least you see here what this Karo syrup can do for you. You see 180 calories per 2 tablespoons, or per tablespoon. It's very low fat, and the rest may interest you before you use it. I had to know C1, which I calculated, I measured it. In fact, what the kind of demonstration you and I will be doing today, you can derive it, but it's very strongly temperature dependent. Could be different yesterday from today. I measured C2 to a reasonable accuracy. Notice that the density of the syrup in terms of kilograms per cubic meter is very close to C2. I mentioned that earlier. They're very close, not exactly, but very close. These steel ball bearings have a density of about 7,800 kilograms per cubic meter. And I'm going to drop in that Karo syrup 4 ball bearings, and they have diameters of 1/8 of an inch, 5/32, 3/16, and 1/4 of an inch. And what I calculated was the terminal velocity as a function of radius of these ball bearings. All of this is on the web. And so what you see here, it is a logarithmic plot. This is the log scale, and this is a log scale. Here you see the speed, and here you see the radius in meters of the ball bearings. And this is my solution to equation number 1 when I substitute various values of r in there. I get the terminal speed like this. And this is the critical speed, which has a 1/r relationship. If you look at this black dot here, then the terminal speed is 10 times larger here than the critical speed. And so notice that when you are at speeds above that you are exclusively in domain 2, and your terminal speed is proportional to the square root of the radius of the ball bearings. This black dot is a factor of 10 below the critical speed. And so you see when you are at lower speeds, when you work here, again, you see that you fall into exclusively in domain 1, and you see that the terminal speed is proportional to r squared. This slope here is +2 in this diagram, and this slope here is +1/2. Our ball bearings are all here. And so we are exclusively operating in regime 1, where the viscous term dominates. Now you could say, well, what is the meaning of this critical speed here? If they never reach that speed anyhow, well, this critical speed for a small ball bearing would be some 100 meters per second. That's about 200 miles per hour. There is nothing wrong with injecting a ball bearing with 400 miles per hour into this syrup, in which case, if you injected it with 400 miles per hour, you would be above the critical speed, and so for a short while would the motion be controlled by the pressure term. But of course, when gravity takes over, then you ultimately end up in regime 1. But that's the meaning of the critical velocity. If you could give the ball bearing such a high speed, then the 2 terms are equal. That's all it means.